we have a beautiful finite group theory exercise here that's very accessible and simple. You don't need to know much group theory at all to understand this. Let G be a finite group with a unique maximal subgroup. I'll explain what that is. Then we're going to show that the cardinality of G is a power of a prime number. So it's quite beautiful that we can conclude something like this, but let's understand what it means to have a unique maximal subgroup. So the way I like to look at it is, if G is a finite group, then the set of subgroups of G has the structure of a partially ordered set, if you like. Okay, so for example, if you have a subgroup H of G, you have a subgroup K of G, you may be able to compare H and K. H may be inside K, K may be inside H, or neither may be true. Okay, so, or both may be true if they're equal. Now, because this is a finite set of subgroups of G, there's going to be a maximal element. Okay, a maximal element is something which is not contained in something bigger, except possibly the whole group. Okay, so the definition is that a maximal subgroup of G, let's say M, okay, so a maximal subgroup M of G is a subgroup M of G such that the following condition is satisfied. So the subgroup M of G such that there does not exist, so this is a symbol, there does not exist H contained in G such that we have H is in between M and G. Okay, so M is in between, H is contained in H is contained in G, and these are strict inclusions. Okay, so H is not, H could be G or H could be M, of course, between M and G, but there are no other subgroups in between. Then we say that M is maximal. Okay, so it's a maximal element of the partially ordered set of proper subgroups of G, if you like, but you can just think of it in that definition. Now, given that maximal subgroups always exist for a finite group. If you take a subgroup like the identity, it's a trivial group, you can just keep getting bigger and bigger as much as you like. If you can't go bigger, the identity would be the maximal subgroup of G, okay? And then G would only have two subgroups, the identity and itself. And you can prove that such groups have prime order, okay? So I've done a video on that, okay? It's going to appear as well, it's going to be in the description on my channel. But in this video, we're going to show that if G has a unique maximal subgroup, then we can conclude the cardinality of G is a prime power. In fact, we can go even further than that. So let's do that. Let's understand how we're going to go. So as I said, here's the proof. So there's a key idea in the proof. The key idea is based on the following. Any subgroup of G, any proper subgroup of G, that's not G, is contained in a maximal subgroup. Every subgroup of G that's proper has to be contained in a maximal subgroup. If itself it's not maximal, we can go bigger, we can find a subgroup in between it and G, and we can keep on going, and because G is finite, that has to terminate. So that will be our maximal subgroup that contains our subgroup of G. Now because of this, another way of saying it is that if G has a unique maximal subgroup, then every proper subgroup of G is contained in that, right? Because that is the only maximal subgroup of G. That means every subgroup has to be contained in that except G itself, of course. So we're going to do this following trick, okay? And a warm-up exercise, as I said, is if G has only two subgroups, prove that G has prime order, okay? So here's the trick we're going to do. We're going to choose, let us choose an element G in G minus M, the set difference. We choose an element of G outside of M. Now, let's consider the cyclic subgroup of G generated by G. This is just all the powers of G, so that, all G power I, where I is an integer. Where a negative power like G power minus 5 is just G inverse multiplied with itself 5 times. Now in this case, we know this is a subgroup of G, but that's so weird. It has to be contained in M, right? But G is not in M by choice. So what does that mean? Just want you to pause and think about that for a second. What can that possibly mean? Well, it means that this has to actually equal to G, because it cannot be a proper subgroup of G. If it were, then it'd have to be contained in M. So we know therefore that G is cyclic. Okay, so this is a beautiful application of using the subgroup structure to conclude something about the group. We know that G is cyclic, and now we're going to complete the argument. So let's complete the argument. We know that G is cyclic now. So we found a generator of G. We know G is cyclic, and therefore we can say that what is a cyclic group, right? It's just the set of powers of some element. So we can write that G is a finite cyclic group, so we can write G is equal to E, G, G squared, G cubed, dot dot dot, all the way up to G power K. Okay, we can say K minus 1 for some K. Okay, for some K at least 1. Okay, K is a non-negative integer. Okay, we can write it in this way. So G has order K in this case. Okay, so K is, let's say that K is minimal, so these are all distinct, then G has order K if you like. And now we know that G has this form. Well, what we can do is we can understand subgroups of G, right? When can G, if K is now the order of the element, then the cardinality of G is equal to K. We want to show this is a prime power. If it's not a prime power, then basically use the fact that if you have any divisor of K, okay, if D is a divisor of K, then what we can do is we can look at the subgroup generated by G power K over D, okay? So look at the subgroup generated by G power K over D. This subgroup will have order D. Since this subgroup has order D, what we know is that every divisor of the order of the group, there is a subgroup with that order. And now we're going to be able to conclude that G cannot possibly have a unique maximal subgroup unless the order of G is a prime number. Why is that? Well, basically, I'm going to finish the proof off here. So basically what we can do is assume that the order of G has two prime factors P and Q. Then what we can do is we can say that there is a subgroup of order P and a subgroup of order Q. Okay, so I haven't used P and Q there, so let PQ be prime numbers such that, you know, PQ divide K, which is equal to the order of G. Because we know that every divisor of the order of G, there is a subgroup with that order, we know that if you take the primes P and Q, then there is a subgroup, so there exists HK subgroups of G such that the order of H is equal to the order of G by P and the order of K is equal to the order of G by Q. But M is the maximal subgroup of G. There's a unique maximal subgroup of G. So therefore H and K have to be both contained in M. But how is it possible? Because by Lagrange's theorem, the order of H has to divide the order of M and the order of K has to divide the order of M. So I want you to explain to me, drop a comment down below, why therefore that's a contradiction, that it cannot be the case that both of these orders divide the cardinality of M, and therefore that implies, because M is a unique maximal subgroup of G, and therefore that implies that G has to have prime power order for one fixed prime P. It has to be the order of that power of that prime, the order of the group G has to be a power of that prime. So thanks so much for watching, and I'm a research mathematician, I do group theory, and drop a comment down below on anything. You know, I'm building new theories on groups, so what better place to learn group theory from? Drop a comment down below what your thoughts are on this video, what you'd like to see if you're learning group theory. Check out my playlist, it's a growing playlist of videos on groups, and all content on my channel. You know, I do everything. I do math across all levels and topics, so, you know, if you're rusty on anything, I give different insights on stuff. You know, I don't just teach it, I explain how to go through the journey and the process. So check out all of that, and I'll see you in the next video. Don't forget to subscribe, like my video, and if you really love my content, please consider subscribing on Patreon. Small contributions there really go a long way to helping me produce infinite free accessible math education, because I currently do everything on my own. So by small contributions there adding up, I'll be able to outsource a lot of the work, focus completely on the math, and deliver lots of high quality math to you. You know, mathematicians generally don't have YouTube channels. They don't have the time because they're busy with a lot of other things. So this is an opportunity. You know, I really want to make it happen. I really want to show the world of math to people. So small contributions on Patreon really help me to sort of edit my videos, outsource things, and create mass content that is really accessible and appealing to large audiences. You know, if you understand this math, you're already in elite level, but why not try to figure out how to make this math accessible to everyone? And that's my long-term vision. So thanks so much for watching, and I'm going to see you in the next video.